Thank you. And yes, as you said, I'm at the final stages of my PhD. Working on this project for 6 years now. My advisors in the PhD are Golan Bell and Ofer Dahan from the Ben-Gurion University in the Boker campus. The title, as you see, it is the measurements and modeling of flux probability distribution in heterogeneous unsaturated zone. And the motivation for this study, okay. So the motivation for this study came from the need to minimize groundwater contamination from the source of agricultural nitrates. Now the problem starts when we have some uncertainty about the amount of fertilizers that needs to be used. And because of that uncertainty, farmers may use a little bit of extra fertilizers. Now the main component of agricultural fertilizers is nitrogen. And once the nitrogen leaves the root zone, it is transported in the unsaturated zone as nitrate. And it may accumulate in the vadose zone, but eventually it reaches the groundwater. Now this problem is an old problem. It's not something new, and it has been studied for several decades now and by many studies. And one of the challenges that still remains around this issue is the need to estimate the fluxes. Now there are several methods for estimating the fluxes in the unsaturated zone. Most of them relies on some kind of measurements in the soil, in the unsaturated soil. For example, this study from 2007 used an array of water content sensors in a sand dune. Now, at the beginning of this study, they considered this sand dune to be relatively homogeneous laterally. But in one of their observations, they found evidence for heterogeneity. For example, here in this figure, we have the arrival time of the first wetting event to each sensor. So each dot in this figure is a depth of the sensor and the arrival time of the first wetting event. Now the precipitation on the sand dune is the same all over the surface. So all the sensors are supposed to have the same process of percolation, the same timing, but they did get some difference in the arrival time. For example, here we have a difference of something like 3 weeks in the arrival time of a wetting event to the sensors of the same depth. So this means that we do have some heterogeneity in the soil properties, even though it was originally considered as homogeneous. Another study by Tuvi Turkeltaub used a similar system in order to measure both water content and solid concentrations. In this case, they used the measured data in order to calibrate a model for estimating fluxes. In this case, they characterize the heterogeneity in the vertical dimension in great details, and other studies may do the same and characterize the heterogeneity of the model in 2 dimensions or 3 dimensions. But eventually, the more heterogeneity we add to our model, the more it is complex and the harder it becomes to estimate the fluxes. Now, if we do manage to calibrate such a model, it can be very powerful in estimating fluxes, but the more complexity we add, the harder it becomes. So the objectives of my study were to establish a database of continuous in situ measurements in unsaturated zone under the roots of an agricultural field in a spatial distribution that can capture the natural soil heterogeneity in considering different fertilizer and salinity levels. And the second objective was to develop a modeling approach which enables estimation of the probability density function of fluxes. And in this case, the heterogeneity is defined by the hydraulic parameters directly rather than by the particle size distribution alone. And this presentation is going to include a field experiment and the main findings from the experiment. And I'm going to present a suggested modeling approach and the methods for selecting the parameters for this approach. And I'm going to show the model validation and some water flux predictions. So the field experiment was done as part of a larger project. This project was led by Danny Kurtzman. The purpose of the larger project was to deal with the problem of reducing the nitrate contamination to the groundwater. And this part of the project, the field experiment, was done in collaboration with Alon Ben-Gal and Uri Yirmiyahu from Gilat. So in the experiment, we had a field which was divided to 20 field plots. We had 4 different treatments, which were based on 2 levels of salinity and 2 levels of nitrogen as fertilizers. And we had 4 irrigated crops. And between those crops, we applied intensive irrigation using sprinklers. The field was monitored by a vadose monitoring system. This system provided measurements of water content in resolution of every 30 minutes. And we had a system of collecting water samples from the unsaturated soil in order to take for chemical analysis in the lab. And the collection of the samples was every 1 or 2 weeks during the experiment. All the samples and all the data were collected through the control panel, which was in the center of the field. So the system was installed under 8 field plots out of the 20, which means that we monitored 2 repetitions of each treatment. And we also applied a bromide tracer at the beginning of the experiment. We applied it as an irrigated solution before the first irrigation of the first crop. And we also collected soil samples for analyzing particle size distribution and bulk density. So here we have the measured water content from the experiment. This is a lot of information here, so I'm going to describe the structure of the figure part by part. So in the legend, each curve has its the number of the field plot, the salinity treatment, and the nitrogen treatment. On the top panel, we have the timing of the irrigation and precipitation. We have the timing of the crops, and the blue curves here represent the cumulative precipitation plus irrigation for each year. Now, in the main 3 panels, we have the measured water content. It's divided to 3 different depth levels according to the location of the sensors. Now, since we had 8 field plots, in each panel here, we have 8 curves of water content, 1 from each field plot. So there's a lot of things to say here about this, but I'm going to focus on one observation. At the beginning of 2017, we applied an intensive irrigation of 200 millimeters in a few weeks. And following this irrigation, we saw increasing water contents in all the sensors. And we can see that it happens first at the upper sensors and later at the deeper sensors. And actually, we have a time lag of about 2 months until we get the last sensor responding after the irrigation. The meaning of this is that we irrigated a lot of water and we received that wetting front that was propagating from the surface down, of course. Here we have the measured concentrations of chloride. The figure is organized in the same way, only now we have 4 panels because we had in each field plot 4 sampling units for water samples. And the depth here are the depth of the sampling units. The first observation I want to show here is that at the earlier part of the experiment, we measured very high concentrations of chloride only on the second depth. And what we think is probably this high concentration of chloride is the chloride that existed in the soil before we started the experiment. And we can see that because we don't see such high concentrations in the upper measurements. The second thing we can see here is that following the irrigation of 2017, we saw these high concentrations decreasing dramatically, and later we saw increasing concentrations in the 3rd and 4th depth levels. This means that the irrigation, the wetting front of 2017 pushed the concentrated chloride downwards, and then we could measure it in the deeper measurements. Now, another thing that we can see here is about the treatment of the salinity. The colors of the markers in this figure represent the 2 different salinity treatments. We had 4 field plots with high salinity irrigation and 4 field plots with low salinity irrigation. Black for the high salinity, green for the low salinity. And what we can see is that we have a clear difference between the 2 treatments, mostly after the 2017 irrigation. And now what we see is obvious. If we added more chloride, we received higher concentrations of chloride. Now we looked for the same observation in the nitrate results. Here we have the concentrations of nitrate nitrogen in the same soil water samples. And the treatments now, the colors of the markers represent the nitrogen treatment. And we look for the difference, the expected difference between the nitrogen treatments, and we found it a little bit on the uppermost measurements and to some kind of a not very wide extent. So we looked at the same data in another way, and here we have again the concentration of the nitrate, but now the colors of the markers represent the salinity treatments. The black markers for the high salinity and the red markers for the low salinity. And what we see is that we have a difference between those two treatments, and we see it only below 3 meters. Now, what the meaning of this is that in half of the plots where we irrigated with high salinity, we measured high concentrations of nitrate. So the first thing we thought when we saw this observation is that maybe it had something to do with the competition between chloride and nitrate for the root apple. But then we looked at the data of the bromide tracer. Now, the tracer was applied as a single pulse at the beginning of the experiment. This orange line here represents the application of the tracer. And it was applied equally in the same field plots. And what we see, if we compare here the two different salinity treatments, is that we again get a difference between the two salinity treatments. In the plots that we irrigated with high salinity, we measured high concentrations of bromide and only below 3 meters. Now, when you see this, you may say that this is not so clear, or maybe what we see here is not very significant. So we tested the significance of what we see here. And we used the Mann-Whitney U test in order to compare groups of data from the two salinity treatments. And we did this test for both the nitrate and the bromide, and we tested each depth level separately. And in each group of data, again, we compared data from the high salinity to data of the low salinity. And what we're looking for in this test is to see if we have groups of data that are significantly different. So what we get is that below 3 meters, we have very small p-values. The small p-values means that we have groups of data that are very different, meaning that the difference between the two salinity treatments in the bromide and the nitrate is significant below 3 meters. So what I'm trying to show here and what I'm trying to convince you here is that when we use different levels of salinity, we get some kind of phenomena that is not only about the plant biology or the solid chemistry, but it also relates to the actual percolation of water. What I'm showing here is parts of the data that I already showed before, and it's the data only below 3 meters. And I want to focus on the arrival of the main wetting event to the deep sensors of the water content. And what we see is that if we compare again the two groups of the two salinity treatments, we get difference in the arrival time of the wetting event. We get that if we irrigated with higher salinity, the arrival of the main wetting event was a bit earlier. So one last observation that I'm going to show you in order to support what I'm trying to say is about the collection of the water samples themselves. This figure is the same figure as before with the nitrate concentrations. Now you may notice that we have some blank areas with no markers and no samples at all. Now in order to collect the water samples from the unsaturated soil, we need to have enough water in the soil. So if there's too little water, we cannot apply enough vacuum in order to pour the water. One thing we saw here is that we have some periods of time where we were able to collect water samples only from the high salinity treatment field plots. This means that the plots that were irrigated with a high salinity, in some periods of time, had more water in the soil, probably. So I'm going to try and summarize everything that I showed until now in this part. In plots that were irrigated with higher chloride treatment, we measured higher concentrations of nitrate below the root zone, below 3 meters, and we saw a higher water percolation velocity and higher amounts of water in the soil. Now, there could be several mechanisms that may explain these observations. Now, this for me is just theory because we did not try to prove any of these mechanisms. Some of these mechanisms may have more relevance or less relevance in this case or in other conditions. For example, one of the mechanisms was suggested by Danny Kurtzman and Daddy Russo, they said that in the case where we irrigate with higher salinity, we may get a different distribution, depth distribution of the roots of the plant, and it may affect in a way that will result in maybe faster percolation of water and more leaching of solutes such as nitrates. Now, the main mechanism which I believe that was in effect in this case of this experiment is actually the reduced clay swelling in porisodic soils. With this process, when we irrigate it with higher salinity, we may get higher hydraulic conductivity and reduced nitrate immobilization within the clays. Now, what we can say is that if we have these observations, they may be an evidence for an enhanced nitrate leaching. We couldn't say for sure because we couldn't measure the actual nitrate leaching, but it could be an evidence. So, so far this was the field experiment and the observations. Now the next thing we need is the ability to estimate the fluxes. So now I'm going to describe the modeling approach. I'm getting the room dark. Okay. I'm going to describe the modeling approach in the process that we had for developing it. So a very common method for estimating fluxes is based on calibrating a model using an inverse solution. For example, if we calibrate a one-dimensional model, then we take the several parameters of the model and we optimize them in order to get the best values of these parameters. Once we get one very good set of these parameter values, we can get a single value of flux. What I'm going to suggest here is to use many different sets of parameter values, and this way we get many simulated values of fluxes. Now, we want to be able to say which values of fluxes have a higher probability. So for that, we are comparing the observed water content to the predicted water content. And using this comparison, we give a different weight for each set of parameters. So the model setup was based on the Hydrus 1D, which solves the Richards equation, the Van Genucht and Moalen. We use the most simplified setup with a single porosity model and a single textural layer. The initial conditions were 20% water content uniformly distributed throughout the profile, but we also used a 3-year spin-up, which means that for each simulation, we started with 3 years of only atmospheric boundary conditions with no irrigations or crops, just in order to get some kind of natural distribution of water content as initial conditions. The boundary conditions were based on the field conditions, and since we had 8 different field plots, then we simulated each of them separately. So the parameters that we were changing in our model are the residual water content, the theta R, the saturated water content, the theta S, the pore size distribution, and the alpha scaling parameter, and the saturated hydraulic conductivity, the KS. Now we are referring to each set of these parameters as a set, and we want to be able to give a different weight for each set of parameters. So we are using this weight function in which the Wi is the weight of each set of parameters, I is the number of the parameter, the LMSE is the root mean squared error between the simulated and the measured water content. This is just the differences between two curves, the simulated and the measured water content. And we have the X, which is a power value that we use for tuning the differences between the weights. I'm going to show an example of how this works. Here we have a probability distribution of water fluxes. These were received using a simulation setup of many sets of parameters. It doesn't matter now which set of parameters, I'm going to show later. But in this example, we get many values of fluxes from many simulations. And the distribution that we see here is some kind of a Y distribution. Now, in order to build this histogram, the value of each bin is the sum of all weights that were given to sets of parameters which produced values of fluxes within the range of that bin. So it's just the probabilities of all the fluxes that were received from this simulation setup. Now, this distribution was created using a power value of 5. So just in order to demonstrate what happens when we use a different power value, in the left distribution, we use the power value of 20, which means that we have a more extreme differences between the weights that we give to the set of the parameters. So the results here, where we have more extreme differences, is a sharper distribution with higher peak. So on the right distribution, we have a wide distribution with a probability of around a maximum probability of around 4%. On the left, we have a more narrow peak with a maximum probability of about 10%. So we want to be able to characterize the heterogeneity using this setup. In order to do that, we're looking for the range and the resolution for each parameter. So the process of choosing the value of the parameters and the range and the resolution included several considerations and a few sensitivity tests. So the first thing we consider is the basic limitations of each parameter, of course. Then we considered an initial estimation, which we created using measurements of particle size distribution and bulk density, and we used the Rosetta model. I'm going to describe this part in the next few slides. Then we considered the convergence of the numerical simulations, and we performed two main sensitivity tests. We test the sensitivity of the weight distribution to the range of each parameter and to the resolution of each parameter. And for these two sensitivity tests, we used full simulation setups with the weights analysis. So for the initial estimation, we used measured particle size distribution from, in this case, it's 72 soil samples. And these are the results. And we took this cloud of distributions, and we created some kind of buffer ranges around the results. And we took all the values from the artificial ranges around the results, and we plugged them into the Rosetta model. The Rosetta model gives an estimation of the hydraulic parameters that we need. And using this analysis, we received these results. We have these three buffer ranges, range 0, 1, and 2. And this is based on the particle distribution. And we also tested different values of bulk density, which is also needed for the Rosetta model. Now, the bars in these graphs are the resulting ranges for each parameter. Each panel here is a different parameter. And the arrow bars are the uncertainties that were received from the Rosetta itself. Now, we took the results that we have here, and we considered the maximal range that we could get for each parameter, and took these maximal ranges as the initial estimation for the following sensitivity tests. So in the next sensitivity test, we used the initial estimation from the Rosetta, and we tested the sensitivity of the results of the weight setup to the specific choice of range and resolution of each parameter. Now here we tested each parameter separately, and we did that using simulations of different setups of the tested parameters with a fixed setup for the remaining 4 parameters. Now, in order to assess these sensitivity tests, we used two different tools. The first tool was the flux cumulative distributions. It's the same example that I showed before. Here we have two probability distributions of water fluxes, which were created using two different setups. We compared here a very wide range of alpha and a very narrow range of alpha, for example. And the results that we can see here are two probability distributions that are apparent, that are clearly very different. Now, we were looking for to see how different these distributions are, and if we can call them this very different, or are they very similar. So in order to quantify the difference, we use the cumulative distribution, which is on the right, and we looked for the maximal CDF difference. In this case, the maximal difference is almost 20%, which is a lot. The meaning of this higher difference is that if we increase the range of alpha from the narrow range to the wider range, we received some unique information that couldn't be achieved using only the smaller range. If, for example, these two setups were resulting in very similar distributions, and the threshold value that we used was 5%, if the maximal difference here was smaller than 5%, then the meaning of that would have been that increasing the range of alpha from the smaller range to the wider range did not contribute any unique information, and therefore the smaller range could have been enough. The second tool that we used in these tests was the weights of each value of a parameter. In this example, on the x-axis, we have the values of a parameter, the theta S in this case, the saturated water content. On the y-axis, we have the sum of weights for each value of the parameter. And here, in this example, what I'm comparing is 3 different setups of resolutions of theta S. We have a setup of 6 values, 11 values, and 21 values of theta S, all of them within the same very wide range of theta S. And what we're looking for here is to see again the difference between the distributions. And in this case, in this example, we see that if we increased the resolution of theta S from 6 values to 11 values, then we get some unique information that created a different distribution. But if we increase the resolution further from 11 values to 21 values, then we don't get much new information. And the meaning of this is that in this example, the optimal setup would be the 11 values. So using these 2 tools, we repeated the test for each parameter separately, and we did the whole process first for testing the ranges of the parameters, and then for testing the resolution of the parameters. And this is the final setup that we came up with. Each parameter has its range and resolution. Each parameter has different number of values. And if we take all the possible combinations for these 5 parameters, then we get 9,900 different sets of parameters. And these are 9,900 different simulations that we use in the final setup. So now that we have the final setup, I'm going to show an example of what we get. Here we have water content in 1,000 days of simulation. And this figure is with respect to only field plot number 1. So the shaded area in this figure represents the maximal range of water content that we could get from all the simulations in each day of those 1,000 days of simulations. The blue curve shows the measured water content from the 3 sensors of field plot number 1. And the dashed curves, the green and the orange curves, show a very specific group of simulated water content curves. And these specific curves are the ones that were given the highest weight from the setup. Now, the difference between the green and the orange curve is the time frame that we use for creating the weights. So on the left side, we have the training period, and on the right side, we have the validation period. The green curve was given weights based on the training period only. The orange curve was given weights based on the training period together with the validation period. What we see in this case, in this example, is that the green curves were able to capture the timing of the main increase of water content very properly. And they also captured the magnitude, the maximal values of the observed water content values. But the orange curves also captured the timing, but didn't capture the magnitude very well. So now we need to try and validate the simulation setup. In order to do the validation, we used the water content values from all the field plots, and we did this process for each depth level separately. So here we have probability distribution of water content values. The distribution is created in the same way that we created them for the fluxes, but these water content values are without the values of the time. But we took these values only from the time frame of the validation period that I showed here on the right side. So we are comparing the predicted water content values in the green distribution to the observed water content in the gray distribution. And the predicted distribution was given weights based on the training period, of course. And now we want to be able to try and say what is the level of fit between these 2 distributions. So in order to test the fitness between the distributions, we use the reliability diagram. And this diagram shows the observed quantile of the distribution versus the predicted quantile. And we are looking for to have this curve as close as possible to the diagonal of the diagram. Now, these 3 diagrams of the 3 depth levels were created using these very specific power values in the weight function. Now, these values are already after the optimization. The optimization was done by testing different values of X, of power, up to values of 200. And the objective function for optimization was the mean of differences of distance between the reliability curve to the diagonal. So for each value of x that we tested, we calculated the mean distance between the reliability curve to the diagonal. And in the optimized values that we got, we had the mean distance between the curve and the diagonal of around 20% for the upper two depth level. And this 20% is a relatively high value. And you can also see that the reliability curve are relatively far from the diagonal, which is not very good. In the third depth level, however, we got a mean distance of 9%, which is much better. And we can also see that the curve is much closer to the diagonal, which is a lot better. So now that we have the validation and the full setup, we want to be able to create some long-term predictions. For that, we created 3 simulation scenarios. We simulated 3 crops every 2 years with potato, corn, and cotton, which is the same as we had in the experiment. And we simulated 1 crop every 1 year with only corn. And the last scenario had no crops with only atmospheric conditions. So we used in each simulation 3 years spin-up and 22 years of simulation, which we used for analysis of the water fluxes. For that, we needed 25 years of measured meteorological data from the Gilat Meteorological Station, and we used repeating irrigation and leaf area index condition based on the field experiments. So now that we have all that, we predicted the water fluxes, the groundwater recharge, at the depth of 3.5 meters. And the weights that we used were analyzed using only depth level 3. This is the depth that received the better validation, and it is also closest to the reference depth for the fluxes that we used. So here we have the resulting probability distribution of water fluxes from the 3 scenarios. On the top panel, we have the probability distribution, and on the bottom panel, we have the cumulative distributions. And just for reference, the annual precipitation in this area is around 250 millimeters. And we can see that the gray distribution, the one with the no crops and no irrigation, is, as we could expect, is all of this distribution is smaller than the annual precipitation, of course. But actually, we have a very high probability, 58% probability to have this bin, the second bin, which is very close to 0. This means that if we did not irrigate and did not have any crops, we most likely don't get any fluxes in the conditions that we simulated. In the other 2 scenarios of the crops and irrigations, we get much wider distribution. And the main peaks of this distribution is somewhere around 100 millimeters per year of water flux. Now, the rest of the distribution has also several peaks. Now, if we did all this analysis using the classic method of an inverse solution and the calibrated and optimized set of parameters, then the result would have been maybe a single value of flux. Now, I don't know where this value of flux would be. I don't know if it would be around the main peaks of this distribution or somewhere else, but it will be only one value, and it will overlook the remainder of the distribution. Now, actually, in these 2 scenarios, we have 50% chance to have very high values of fluxes. And if we only had one value of flux, then we would miss all the rest of the distribution. Another interesting thing that I can show here is from the ratio between the cumulative flux and the total input of water in each scenario. And once we calculated this ratio, we can see that the distributions of the 2 irrigated scenarios are very similar. The meaning of this is that in the conditions that we simulated, the field conditions that we took, and once we had any irrigation and crops, it didn't matter which crops or how many crops we used, and the distributions are practically the same. This means that the amount of flux depended mostly on the input of water. Okay, so I'm going to summarize everything that I discussed. Then we had a field experiment that tested the effects of different salinity and fertilizer levels on the water content and solid concentrations. In this experiment, the measurements showed that irrigating with high salinity resulted in relatively higher percolation velocity and higher nitrate concentrations. And this experiment also provided a database which represented the heterogeneity in soil properties. And using this database, we created a modeling approach that considers different weights for sets of parameters. We also developed the methodology for the parameter selection, and using all that, we created the long-term predictions for fluxes with different scenarios. Okay, so there are many people I can thank, many people who contributed to this project in the field and in the lab and in brainstorming and in writing. So thank you to all these people. And this is some graphical outline of everything that I showed, and thank you for listening.
Thanks, Gal, for the nice presentation. Any questions?
I have a question, may I ask?
Yeah.
Okay, thank you, Udi. Thank you, Gal. I'm just wondering, I mean, I understand that the effect of salinity on clay swelling is a very old issue, which was studied in very many studies. But my question is, with a level of salinity you are using, how does it fit to the lab studies and the batch experiment? How significant should be a reduction of the swelling of clays? Did you try to compare it somehow? Yeah, I remember people were using very high salinity solutions, really high, like molar concentrations. And how comparable is salinity in your case?
So we did not test the process of the clay swelling, but what I can show, I can just show the values of the different salinity levels that we used. Okay, so in our experiment, we used in the plot of the low salinity level, we used the water from the main pipeline, which is mostly desalinated water with around 50 to 80 ppm of chloride. And in the increased salinity, we increased around 300 to 400 ppm of chloride. It was a little different in each crop, but these are the main range of the value. So I cannot clearly say for sure how which values would affect how the process of clay swelling, but I hope that somebody will test it in this context maybe.
But maybe it was done. I'm just asking.
Maybe
you can just compare with literature and check if that salinity level was sufficient to affect swelling.
So I don't have an example that I know of. Maybe it was done, but I don't know which study tested this specifically.
And another question is, was there calcium carbonate in soil or not?
Calcium carbonate?
Yeah.
We did have calcium. We didn't measure the carbonate, I think. But I know that we did have significant concentrations of calcium. I cannot tell you how much, but we have the data. We just didn't compare it in this case.
But you have to know if it's calcareous soil or not. I mean, what is the gear content? What is the calcium content in soil? I'm asking because nitrate actually might absorb on calcite carbonate, and maybe not only calcite carbonate, also because of the calcium presence of bridging. It's not exactly anion, which means it may absorb. And then might be hypothesis you indicated in the beginning about competition with chloride. Maybe there is a place for that also.
So you're saying that if we have different levels of chloride, then the competition in the absorption will be different.
Yeah, you wrote it by yourself, and actually it is very easy to check in the lab test, in very simple lab test, if it is any place has any significance. Maybe it's not significant at all.
Yeah, I agree. It could be interesting to test that. Yes.
Thank you. Thank you.
Thank you.
We have some more time. Anyone else would like to?
I have a technical question.
Okay.
I was wondering about the procedure running the Hydrus 1D many times. Did you use MATLAB with the connection with the Hydrus?
Yes, we use MATLAB. Yes, main parallel execution.
And you, okay, thank you. Thank you very much for the presentation.
Thank you.
Asher, did you raise your hand? But I saw.
Yeah, sure, I can't hear you.
Asher, we don't hear you.
Now?
Yes.
Yeah.
Okay. So about Michael question, this soils in Gilat is about 10 to 15% of carbonate.
So it's
So
a huge amount.
yeah, so it's not
Huge
acid. Now about the salinity and nitrogen, both of them, the salinity is not very high for the crop, so this was very challenging, and the results are very interesting because if there was much higher nitrogen salinity, like 700, 800, then the main effect was on the crop. But in this experiment, there was very slight effect of the treatments on the crop.
Yeah.
The same for the nitrogen.
Yeah,
And,
I didn't show the data, but there was not a very large effect on the crops of all the treatments.
Yeah. So all the conclusions and so on are more on the modeling exercise in the transport of water, but not without the main effect usually of high fertility relative to high nitrogen relative to low nitrogen, or high salinity. And so it's very interesting. Thank you for the.
Yeah, we didn't get to the part where we add the solids to the model, but of course the intention that this approach can be applied with the solids as well.
Yeah, maybe when, for example, in the permanent plot in Bet Dagan and the Gilat that were terminated about 30 years ago, there were treatments of low nitrogen, and then the low nitrogen affected the leaching of chloride to the depths because of the much lower uptake of water by the plant. So
yeah,
here,
this may relate to the
for,
theory by Dadi and Dani.
Yeah,
this
so
mechanism, probably.
so here what's interesting is it's the effect of a very narrow range, not extreme conditions, not extreme salinities, not extreme nitrogen.
Yeah.
You hear me?
Yeah. Danny, you wanna ask?
Yeah. Okay, thank you for the nice presentation. I didn't follow exactly all of it, but just a few. First, I want to say this whole project was in the context of Israel having more desalinated water, which is of much lower salinity, and its effect on the, let's say, the main or the biggest agricultural contaminant, the nitrate. So the rationale here was maybe there's an opportunity for less leaching due to the reduction in water salinity, both in freshwater irrigated and in effluents. Both the salinity significantly went down in certain places. Of course, in certain places it didn't change if they don't use not connected to the national water carrier, so they don't have desalinated water.
Mhm.
That's first. So we see the results have the idea, have some we get from the Gilat soil, from the loss of Gilat, which is certainly a very important area, agricultural area. We see that there is this phenomena of less leaching when irrigated with the desalinated water, while more leaching, both as we saw here in the observations, and as Daddy and me proposed when by simulation experiment by simulations research concentrated on simulations, we see that when you irrigate with more saline water, the uptake in the shallow parts of the root zone is small. More water percolates, increasing the water content as you showed here. And when we increase the water content, of course, we increase the unsaturated hydraulic conductivity, and then increase the fluxes, generally fluxes that go down. So we showed it on a simulation, simulating an orchard, a citrus orchard, but generally it's the same. Another thing I want to say, we did similar experiments in this project in pots with sandy soil, much more sandy soil than Gilat's less. And we found less of this effect in the sandy soils. The salinity, especially the salinity we used, which was not very high salinities, but still the salinities where we're used to from Lake Kinneret water, and somehow higher. And we didn't see much of this effect in the sandy, actually in sands in pots. Yeah, that's about it.
Thank you, Danny.
Okay, so if no more questions, then I would like to thank you again, Gal,
Thank you, Udi.
and see you next week. Thanks.
Thank you, everyone. Goodbye.
Yeah.